Hello everyone, welcome to the course on Introduction to Multi-Agent Systems. In today's lecture, we'll talk about some basics from graph theory. So before we get started with the technical definitions and notations, let us start by discussing a practical example. The image that we see here is the city of Königsberg. Now the city of Königsberg has a river Pregel which divides the city into four parts. The parts B and C are the land masses of the city, and A and D are two islands in the city. And the land masses and the islands are connected to each other through exactly 7 bridges. Now, around the year 1736, the then mayor of a nearby city, Carl Gottlieb Euler, posed this question to the famous mathematician Leonhard Euler, asking him, is it possible to do a round trip through the entire city while traversing each of the bridges exactly once? Meaning, if we start from point A, then we go around the whole city such that we traverse all of the bridges that are there in the city. But while doing so, first, we must come back to A. Second, in the process, we must have covered all of the bridges only once. So now, I ask the students to pause the video here and try it out for a few seconds. Try to see if you can arrive at a path which satisfies these conditions. Okay, now, how much ever you try, you will not be able to arrive at a solution because, in fact, the solution to this problem does not exist. Now, while trying to answer this question, Euler actually started the field of graph theory. So, how is this problem defined in a graph theoretical manner? Let's see. In order to do that, the land masses B and C and the islands A and D are simply denoted as points, and every bridge which connects two vertices are actually denoted as an edge in the network. Note that the points that are given here are referred to as the vertices. So let's look at this figure and let's try to arrive at the graph of it. So let's say this is point C, this is A and B, and we have D. A and D being again the islands and B and C being the land masses. Now every edge is simply a bridge in the city connecting the vertices. If we can see, A and C are connected through 2 bridges, and again A and B are connected through 2 bridges, and A and D are connected through just 1 bridge. Similarly, C and D are connected through just 1 bridge, and B and D are also connected through just 1 bridge. Meaning, this is what the question looks like. So now, if we try to traverse along this bridge, along this graph that's given here, such that, let's say, for example, we start at A, can we come back to A such that we have actually gone around every edge, all of the edges first, and second, all of the edges just once. So let's see what it looks like. Now I cannot move any further from here because any further movement would lead to a repetition of an edge. Meaning, again, this is not a feasible walk because one of the edges is untraversed. We can try several other configurations, but none of them will work. So now, let me ask this question to the students here. Can we actually add a bridge in Königsberg so that the entire city becomes traversable via the bridges, such that the bridges are traversed only once? Meaning, So the question says we need to add only one bridge. So the answer to this question is in fact yes. It is possible to add just one bridge so that the entire city now becomes traversable in the desired manner. So where exactly should we add that bridge is something, please try it out. It's not very difficult. So now this is just one example where we saw how a problem can be represented using graphs. But graphs in fact can actually be used to represent numerous real-world problems. So first of all, how do we formally define graphs and what are the real-world examples that they are applicable for? So let's try to see that. So formally, what is a finite graph? A finite graph denoted as G is built upon first by a set V which consists of all of the vertices in the graph, where we denote any ith vertex by the notation Vi. The second thing that it consists of is the set E. What is the set E? It is simply the set of all the edges in the graph. Now, any graph G is always defined in conjunction with the two sets V and E. Now, a graph can be, as we have already seen before, a graph can be either directed or undirected. When is a graph undirected? When simply all of the edges that are there in the graph are undirected in nature. And when is it directed? It is directed when the edges have directions assigned to it. What is an example of a directed network? So we have talked about it before. Suppose we have a set of robots which have a limited field of view. Then, so let's call it robot 1 and robot 2. Now, while robot 1 can actually see robot 2 is not able to see robot 1, meaning the edge that we construct here will have a direction to it. But now imagine the scenario when they have omnidirectional cameras, meaning they can look at a 360-degree view. In this case, both R1 and R2 are actually able to look at each other. While this makes the graph directed, this will always result in an undirected graph. So let us see some more examples where graphs can be used. So the image that we see here is of a transportation network of the Delhi Metro. So in this particular example, the nodes are the vertices. So note that vertices and nodes are used synonymously in graph theory, and I'll be using both of them throughout the course. So in this particular network, what are the vertices? They are simply the different stations in the city. And what are the edges? The edges are simply the path connecting the two stations. Yet another example would be a social network. So the particular social network that we see here is that of a network from Facebook. What we see here is that all of the agents or the users which are using Facebook are denoted as the vertices or the nodes, and the edges connecting them simply refers to whether or not they are friends with each other or whether or not they are interacting with each other. Yet another example is that of the spread of COVID-19 pandemic. Now, this is also something that can be used, that can be represented using graphs. How? So the figure that is shown here simply represents how COVID-19 actually spread globally. And this data is collected using the global tourist network. So depending on how the tourists traveled, COVID-19 spread accordingly across the globe. And again, this is how it can be represented graphically. Now, all of the three networks that are shown here actually look quite different from each other. But in general, there are some basic graph structures that we keep using very, very commonly. So let us look at a few graph structures like that. So let's start with some very basic undirected graphs. The first one is a complete graph. What is a complete graph? In such a graph, there exists an edge between every pair of vertices. For example, in this graph, which has 4 vertices, we see that any 2 vertices that we pick has an edge connecting them. Yet another commonly used graph is a path graph. Now in the path graph, all the vertices are generally arranged in a sequence joined by the corresponding edges. What does it look like? It simply looks like a straight path as shown here. These are the vertices arranged in a sequence, and we have just one edge connecting all of them. The third commonly used graph is that of a complete bipartite graph. Now, bipartite graphs are something that appear extremely commonly in social networks, in sociology, and in several places. So, what is it? Now, in a complete bipartite graph, the set of vertices V gets divided into 2 parts, into 2 disjoint sets, such that every vertex, so let's denote it. Suppose this is set V1, this is set V2. The set of all the vertices is simply V1 union V2. Now, in a complete bipartite graph, any node that we pick here will have a path to every other node in V2. And this property holds for all the nodes of V1. So, what will such a graph look like? This is what it will look like when we have, so let's name them. So, any Vi and Vj we pick from here, we will see that there exists a path connecting them. However, note that there will not exist a path if we take any 2 elements belonging to the same subset. For example, 1 and 2 do not have a path with respect to each other. So, in a complete bipartite graph, it is mandatory for any node or any vertex from one of the subsets to have a path to every other. But when we relax it to be simply a bipartite graph, then all that we say is, when we relax the condition of the graph being complete, then again we divide the set of vertices into 2 parts V1 and V2, and edges can exist only between the subsets. But if we pick any vertices inside a particular subset, then edges cannot exist between them. So, this is a bipartite graph. Some other very simple graphs. First one would be a cycle graph. In a cycle graph, it is simply a path graph whose starting and ending vertices are the same as shown here. Yet another kind of an undirected graph is a star graph. In a star graph, we actually have a center vertex. What is the role of a center vertex? Now, any edge in the network actually connects the center edge to every other vertex in the network as shown here. Now, such networks are also very commonly used. For example, when we have a central node connecting them, this can generally be used to decide, especially in the directed counterpart of it, how consensus drives in a network. So, these are something, the applicability of all these graph structures is something that will be covered eventually in the course. But now let's look at some basic directed graphs as well. So, the directed notions are very similar to the undirected part, with the only difference being that the edges now become directed in nature. For example, in a complete digraph, we see that between any 2 pairs of vertices, again we have an edge in both directions. And in a path digraph, so just to remind you, a digraph is simply a directed graph. So in a path diagram, it's simply a path graph which has directed edges. Similarly, a cycle diagram is again a cycle who start a cycle graph with directed edges. So these are some basic graph structures that we will keep using throughout the course to illustrate various distributed algorithms. Now, let's think about a social network. Now, a social network generally is a very large network. In such large networks, generally the interactions among people become localized in nature, leading to the formation of subgroups within the large group. And this is what it generally looks like. So again, this is the same Facebook network which we saw before. So if we zoom in and see, we can clearly draw out some close-knit communities within this network. For example, we see that this set of people seem to be more tightly knit with each other than they are to the rest of the network. Another such subgroup would be this, and yet another one would be this. So now generally, subgroups within the large group get formed quite often. So how do we go about defining a subgroup formally? Now in general, that's known as a subgraph of a graph. And formally, how do we define a subgraph? It goes like this. Let us start with a graph G, which has its own vertex set and edge set. Now any digraph G prime consisting of the vertex set V prime and E prime, it is a subgraph of the large network G only when it satisfies these conditions. What does this say? That the set of vertices that G prime has should be a subset of the vertices of the larger graph V. Similarly, the set of edges E prime must be a subset of the edges of the larger graph G. That's it. The definition is as simple as that. Now let us try to define some very useful kind of subgraphs that again we will be using while designing distributed algorithms. The first one is an induced subgraph. So what is an induced subgraph? Again, let us start with a digraph G, vertex set V and E. A subgraph G prime becomes an induced subgraph only if, first of all, the set of vertices is a subset of the set of vertices of the larger graph, and E prime contains all the edges in G between any two nodes in V prime. So let us try to understand this definition through an example. Let's start with this directed graph shown here, which has about 7 edge nodes. And let us look at this subgraph. Now the subgraph that is shown here, so certain edges have been deleted here and the solid edges form the subgraph. So it's effectively just this. Now, is this subgraph a candidate for an induced subgraph? In order to do that, all that we need to check is, let us pick any two subsets, vertices, let's say 2 and 3. Now, if we go back to the original graph, we see what are the edges connecting 2 and 3. All of those edges have to be in G prime. We see there's just one edge and that edge is represented here. So it is fine. Let's look at 5 and 6. If you look at 5 and 6, again in the original graph there's just one edge and the same edge is retained here. Now let us look at 2 and 6. If you look at 2 and 6, we see that there's again one edge here, but when we come back to G prime, that edge is missing, meaning it is not an induced subgraph. However, when we look at this network, if we check it, we will see that any two vertices that we pick from here, whatever are the corresponding edges in G, all of the edges are here in G prime, meaning This in fact is a valid induced subgraph. Now similar to induced subgraph, we have one more kind of a subgraph which is known as a spanning subgraph. So let us define a spanning subgraph. Again, we start with a larger digraph G with vertex set V and edge set E. Now any digraph G prime consisting of V prime and E prime, it becomes a candidate of a spanning subgraph only if, first of all, G prime must be a subgraph. Second condition is that the number of vertices between G prime and G must be the same, and that is the only requirement for a subgraph to become a spanning subgraph. So again, let's quickly see a few examples. We start with this original network G, which is the same network which we saw before. And this is a second network, G3 prime. So if you look at this network, is this network a spanning subgraph? Now we need to, let me highlight the subgraph again. So what do we see? We see that some of the nodes are getting left out, meaning it is not a valid spanning subgraph. Let's look at yet another example. If we see here, let's first try to trace it out. If we look at this network, we see that V prime is exactly equal to V, meaning this is a spanning subgraph. Now, the notions of spanning subgraphs help us a lot in the analysis of distributed algorithms, and in some ways they also help us in figuring out which are the dominant subgroups within a large group. With this, we come to an end to this lecture. These are some of the references from which we got the images of the real world systems, and we'll talk more about the basics of graph theory in the next lecture. Thank you.